Dear students, so far we have learnt about combinational circuits in the earlier videos. But then I did not define what I mean by a combinational circuit. So let's create a simple one and then I shall explain you the same. We have this AND gate and let me put in the two inputs. From now on we shall not be using LEDs anymore to display the outputs. We shall rather be using this output tooltip to show the value in the binary. Now as you can see over here, when I put 0 and 0 as the input to the AND gate, the output becomes 0. The moment I change both of them to 1, the output immediately changes to 1. So a combinational circuit is one in which the output at a particular instant of time depends only on the values of all the inputs at that instant of time only. The output does not depend on the past values of the input. Okay, so that means that such kind of combinational circuits do not have any memory involved in it, which will capture the previous possible state of inputs. But we do require certain circuits which whose output we want to depend on the present set of inputs as well as the past set of inputs or certain outputs as well. So such circuits which depend on the past values also are called the sequential circuits. So in the circuits elements box, if you click on sequential elements, you will get a list of a lot of these elements, but in this video I shall only be talking about the important one, that is the D latch. So this D latch has 4 inputs, as you can see, 4 ports. The first one is the D port, which is the normal input. This one is a clock port, okay, the clock, and these two Q and Q bar are the output. Let us put in some inputs, and in this clock for now, in order to demonstrate the functionality, I will be putting in my own clock. That means I will toggle it myself and try to explain the behavior to you. For the output, I take the output tooltip. Okay, and now we shall also use certain waveforms, and in order to visualize these waveforms, we use these flags, which are like oscilloscopes that show the values of the wires at all instances of time. So this you can see is having this port at the right side. I click on orientation and click on left. I'll do the same with this one, orientation left. Alright, now let's look on the timing diagram. In order to start, I press this reset button. As you can see, these are the values that are popping up on the waveform window, and in order to understand these waveforms better, let me rename these waveforms. So this is the input, so I click on this and select the debug flag identifier and write it as D in. This is the clock, so I click on F2 and rename this as clock. This is the Q output, this is the Q bar output. So now you can see over here that all our waveforms are visible. The D in, the clock, the Q. D in is at 0, clock is also at 0, Q is at 0, and obviously Q bar is 1. Now let's look at this. This latch also has a value showing in between, inside it, which means that the latch has stored a value 0 in it. Okay. Now see, the clock is 0. So if I try to change the value of D from 0 to 1, there is no change in the output. It is still showing 0 and 1. See the very difference? I once again change 1 to 0, and I once again change 0 to 1. There is no change in the output. You see, this is a very big difference. Okay, the clock is 0, so you might not be convinced that this is a sequential circuit. but you see the value 1 is stored inside it, right? Now what I shall do, let me change it, the clock from 0 to 1. Okay, I have changed the clock from 0 to 1. Things are the same as it is. All do try to focus on this as well. D in is 0 and now I change this to 1. You see I have changed it to 1, and since the clock is high, you can see Q has also changed to 1 and Q bar has changed to 0. Okay, now let me keep on changing this D in from 1 to 0. You see it has become 0 once again. I change it to 1, it becomes 1. I change it to 0, it becomes 0. So let me do some random fluctuations. So you can see these fluctuations are visible in the Q and Q bar as well. Okay, so let me keep it to 1 and put the clock to 0. Now you see the clock has been kept at 0, but the output is still 1. Okay, 1 is being shown over here, and the latch has stored a 1. Now you see, even if I try to change this D in, the internal value of this latch does not change, and you see the output is still the same. So this is a memory, isn't it? So whatever was the last value captured in this when clock was 1, you see when clock was 1, the last value that it took, that D in took, was 1, and that value has been stored or saved in the latch. And you can, in order to show you once again, this is a latch and this clock, you see the moment clock is 1, this, as long as clock remains 1, this D in variation automatically shows up in the output, and the moment clock is 0, the variations don't show in. So clock is like a switching, or it's like a gate which says that when clock is 1, I allow everything to flow from D in to Q, and when clock is 0, it says that no, D in cannot flow from D in to Q, and whatever was the last value stored in the latch, whatever was the last value of D in when the clock was 1, that value gets stored in this latch, and this is how the latch behaves as a memory or a sequential element. Now I shall show you something called the flip-flop and try to explain its difference. Okay, so you see the sequential elements over here. Here is the D latch and this is the D flip-flop. Okay, so let me keep everything to 0. This is D in, this is the 0, this is the Q input, this is Q bar. Okay, this is the enable. Why enable? In certain chips, in certain circuits, you have lots of D flip-flops, and sometimes based on certain conditions, you may want to use this flip-flop or you may not want to. So that condition, if that's true, then the enable has to become 1. But in our case, we always want the flip-flop to be on, so that's why we keep the enable to the high voltage. Otherwise, depending on your application, if certain signal says that the flip-flop has to be off or on, then that particular signal has to be driven to this enable port, and then this is something called a preset. But actually, if you set preset to high, then the value over here turns to 1, but this doesn't seem to be working in this in this environment. So for the sake of doing, let me connect this, and this is something called the asynchronous reset. So we shall demonstrate the function and definition of this asynchronous reset very soon. So let everything go to 0. Fine, you can, over here you can also change the speed of your simulation. So like everything, now the simulation is at 1 second. Fine, so you have asynchronous reset as 0, all of them are 0, so everything is clear. Now you see I once again try to change D in. So I keep trying to change D in, and D in, as you can see over here, has changed, but there is no reflection of the same in this Q and Q bar. Clock is at 0. Now you see D in is at 1. And now what do I do? Let's change the clock from 0 to 1. The moment I have changed the clock from 0 to 1, after some time this Q becomes 1 and Q bar becomes 0. So D in has captured this value. Now you remember in the latch I tried to change D in and the corresponding change was visible in Q. Now let me try to do those changes. Okay, you try to see this. D in has changed, but Q has not changed. It's still at 1. I try to change D once again as much as possible, but Q and Q bar does not change. It remains fixed to 1 and 0. So that means that this is no more behaving like a latch. It actually behaves in a different way, and I shall show you. Now you look at this asynchronous reset. The moment I click make this 1, look at this, the Q is initially 0, the stored value Q is 1, the stored value is obviously 1. The moment I switch on this, okay, so this is actually connected to a permanent 0, so it will never be changing. So let me put in the original 1. Fine. So now look at this carefully. I have this asynchronous reset, and the moment I press 1, the value inside this has changed to 0. Even if I change this, I have put it to 1, so this one goes to 0. Clock is still 1. I change it to 0. I try to change D in. There is no change in it. So how should I change? Let me put clock to 0 and again try to see if any change is possible. No change is possible. Now you see Q is stored at 0, and if I try to change D in to 1, and look at this, the moment I change clock from 0 to 1, this value is being captured. I change it to 0, no value, that value is not captured. I keep it to 0, I again change it. Okay, so have you understood the logic? Now let me pause this a bit. Fine, let's look a bit deep into this timing diagram. D in over here, clock is 0 over here. D in changes from 0 to 1 at 509, and D in remains high. The very moment when clock changes from 0 to 1, at that very instant Q also changes from 0 to 1. That means this clock's rising edge is actually used to determine the which value of D in should be captured. So the value of D in present at this rising edge of the clock is being stored in the flip-flop as a output. Now you see, even when the clock is 1 and D in has changed from 1 to 0, that change does not reflect in Q at all. Okay, that change from 1 to 0 does not reflect into Q despite the fact that clock is still 1. So that means that this circuit is not dependent on whether clock is high or low. In latch, when the clock was 1, then all the changes in D was visible in Q. But in this flip-flop, the change is visible only in the edge. When this clock changes from 0 to 1, which is called the rising edge of this clock, the value at that instant gets stored in the flip-flop. So this is the difference between the flip-flop and this latch. And you also see once this D in falls to 0 and this D in falls to 0 and this clock changes from high to low. So you see this edge is actually called falling edge, and in this falling edge also we don't have any change in Q. Now after I again make a rising edge over here, D in is 0, Q was 1 over here. Now at this rising edge, the D in 0 value gets captured, and this causes the Q to transition from 1 to 0. So this is the rising edge flip-flop. Okay, this is the flip-flop. Flip-flop captures the value of the input at the rising or falling edge depending on the edge shown over here. This triangle actually shows that this is an edge triggered flip-flop. Although you will see this latch also having this triangle, but it is not the case. If you actually look into circuit diagrams, let me show you the flip-flop. If you look at this D flip-flop, this is the triangle that shows that this is an edge triggered. And you can also look at the images or the truth tables. Okay, so you see over here, when the clock is at rising edge, these are called the rising edge. From 0 to 1, these transitions are called the rising edge. When the clock changes from 0 to 1 in the rising edge, that particular value of D gets stored into Q, which you can see over here. D is 1. At this rising edge, Q changes from 0 to 1. At this rising edge, D is 0, Q changes from 1 to 0. Okay. So I hope you have understood very well about this latches and flip-flops. Thank you.